Six volt. Gotta have an adapter in here that'll work. 9 volt. Never the right voltage. 5 volt. Hi, this is Jeff from the Ozark Mountains. That's in Missouri, in the USA. Well, I think we all have one of these. A big old pile or box or drawer of miscellaneous wall warts that we've collected over the years. The devices these went to died or got lost or got separated from the power adapters during a move, that type of thing. And, then we run out and we buy a new piece of vintage computer gear and we want to charge this thing up. And we look in our pile of adapters here to see if we have something that'll work. And maybe we need to, purchase one. And what do we get to fit our old gear like this? In this video, we'll concentrate on finding just the right power adapter for our vintage gear. And we'll concentrate on portable, rechargeable, battery-powered things, but we'll touch a little bit on the basic characteristics of these power supplies and what to look for and how to find out if one of the miscellaneous ones you have will work or what to look for in a new one. Well, let's jump right in. Thanks to PCBWay for sponsoring this episode. They offer an excellent quick-turn PCB prototyping service, which now has a free upgrade to the 150-160 temperature range. They also offer a wide range of services that allow you to go from idea to a finished product, including CNC machining, 3D printing, injection molding, PCB assembly. Go on over to PCBWay.com/OEM to find out more. As you know, wall warts come in all shapes and sizes, but we can break them down into two main categories. First, we have the AC output variety, and we have a DC output variety. But we can also further break down the DC output into two subcategories of regulated and unregulated. And we'll get into the details about the differences between those in just a bit. First, let's talk about some important mechanical differences. Most wall warts that you'll find will have some sort of barrel connector like these, and they differ in the outside diameter, the inside diameter, and even the length of the barrel. But some old devices used a 1/8 inch or 3mm mono phone plug like this guy. And just to make things more interesting, not only do you have all these different diameters and even different styles, but they can also be wired in either polarity. You can have the tip be positive and the barrel be negative, or vice versa. Both are used now and in the past. This is an important point, as you can damage some pieces of equipment by having the plug wired backwards. Back to the electrical differences. We already talked about the biggest difference, that is between an AC output and a DC output adapter. And of course we want to get an adapter that has the correct output voltage and current rating, and generally we want to match the original adapter as closely as possible. I had mentioned that there are two main types of DC output adapters. One is the regulated variety and the other is unregulated. To get an idea of what I'm talking about here, I've popped apart a real vintage unregulated DC adapter, and we can see what's inside. We have a transformer here, we've got 4 diodes to turn the AC into DC, and we have a big filtering cap here which is leaked all over the place. Now, a regulated adapter is going to have all these same parts, plus some sort of voltage regulator chip like this 7805, and normally these are mounted to some sort of heat sink, and there's a few other capacitors thrown in there as well. And while a regulated adapter will output close to its rated voltage, whether it is connected to the piece of equipment or not, an unregulated adapter like this guy is an entirely different story. And this causes a lot of confusion and potential problems for folks trying to find a modern adapter to fit their vintage gear. If we look at the label of this Epson HX20 adapter here, we see it tells us the input is AC 120 volts, the output is 6 volts DC at 600 milliamps, and they were nice enough to tell us the polarity of the connector. Now, since this is an unregulated adapter, what this output rating means is that when we are drawing about 600 milliamps from this adapter, the output voltage will be about 6 volts. If it's not connected to anything, if we got it plugged into the wall but we're not connected to the HX20, the output of this is going to be about 20 or 25% higher. So for example, this 6 volt adapter, when it's not connected to the machine, is going to be outputting about 8 volts. That's perfectly normal. Let's go ahead and demonstrate this here on the bench. Here is our experimental setup. We have a breadboard with 22 330 ohm resistors in series. Right now I've got half of them disconnected. The red meter is measuring the voltage that we have across our load, and the blue meter is measuring the current that's going through it. And powering this, we have our Epson power adapter we looked at earlier, which says 6 volt at 600 milliamps. So we'll plug this in with the load disconnected, and we'll measure what the open circuit voltage is, and then we'll measure the open circuit voltage, or the voltage and current, with half load and with a full load, which should be around 0.4 amps. Okay, here's our first sign of this being an unregulated adapter. We have 8.6 volts open circuit. And if we connect this, with a 200 milliamp draw, it's down to about 6.9 volts. And with about a 400 milliamp draw, it's right at 6 volts. So our adapter, when it wasn't powering anything, was outputting about 8.5, 8.6 volts. And when it is supplying 400 milliamps, 0.4 amps, it drops to about 6 volts. But why is this? Well, this is essentially our circuit right here. We have our wall wart connected to our load. We're measuring the voltage across the load and the current through it. Open circuit, without our load connected, our wall wart is outputting 8.5 volts. With a 0.4 amp load, it's outputting 6 volts. Well, why is this? Well, we know it's an unregulated wall wart, and we can think of it as having a resistor in series with the output of the wall wart. This is an easy way to model what's happening here. It doesn't explain the full story, but it's close enough for our purposes. So remember again that we started out with 8.5 volts open circuit, 6 volts with a 0.4 amp load. That's a difference of 2.5 volts at 0.4 amps. Using Ohm's law, voltage equals the current times resistance. We can rearrange this to solve for resistance. Resistance is voltage over current. We had a 2.5 volt drop, 0.4 amps of current, and that comes out to about 6.25 ohms. So this circuit is acting like, our wall wart is acting like, there is a 6.25 ohm resistor inside the wall wart. This has to do with how the transformer acts under load and things like that. But this gives us an idea of what we would need to do if in our application we needed a modern regulated supply to emulate how one of these unregulated supplies worked. According to our theory here, we could figure out the equivalent in-series resistance, add a resistor in series, and it would act like our unregulated supply. Let's try that out. Okay, now instead of our wall wart, I've got my bench power supply hooked up, and you can hear the fan on it whirring. It has a limit on the output of 8 volts, so I've got it set to that. Right now it's disconnected, and I have a 6.2 ohm resistor in series with it. And if we connect this to our load here, under half load, about 200 milliamps, it's already dropped down to about 6.5 volts. And if I connect the full load, you can see our voltage just dropped a little lower this time, about 5.5, only supplying 350 milliamps. But remember that our modern regulated power supply, my bench power supply here, will only go up to 8 volts. So if we look at our calculation here again, and if instead we did 2 volts divided by 0.4 ohms, 2 volts divided by 0.4 amps, we'd come up with about 5 ohms. So I've got a 13 ohm resistor here, which I will put in parallel with our 6.2 ohm. That'll result in about a 5 ohm resistor. And you can see we now are acting very much like our wall wart. We've got about a 6 volt output with about a 0.4 amp current. So we've made a modern regulated supply work as badly as a vintage unregulated supply. Now there are cases in battery charging applications that this might be useful to know. Now you might be thinking, well, you know, why fool around with all these old-fashioned unregulated power adapters? Why not use a modern wall wart that is regulated, and we get a 6 volt adapter, we get 6 volts out of it, none of this higher voltage, lower under load stuff, and you know, everything will be good. So let's test that. I've got a modern 6 volt wall wart here, which I'll plug in, and I've got half load connected, and we've got about 1800 milliamps, and it is about 5.8 volts. Ignore the negative, it's just the polarity of the connector on the adapter here. So we've got a little less than 6 volts because there is a bit of voltage drop in all the wiring I've got here. And if I connect the second half of the load, you can see we've got about 360 milliamps, and our voltage dropped a little lower. Again, that's just in the wiring. And you might think, okay, well, you know, so maybe we've got a little less than, you know, our 6 volts, but maybe that's okay. We're not going to damage anything. Maybe our device will work fine like this. It might, and probably not, especially if it's a rechargeable device. So we'll have to get into studying some schematics and things like that to find out why and see where the problem lies. Now let's look at some actual vintage machines and the charging circuitry that they have inside. Here we have an Epson HX20, and it belongs to this adapter that we've been using for our experiments, the one that says 6 volts at 600 milliamps. The charging circuitry in it consists of this. This is straight out of the manual. As you can see, it's very, very complicated. We have the positive and negative from our adapter here. Goes through a diode. This is for reverse polarity protection, and a current limiting resistor, and that charges up the battery pack. This is a 4-cell NiCad, 4 times 1.2 volts, 4.8 volt battery pack, and this is where the power goes out to the machine. So when we apply our 8.6 volt adapter here, when we plug it in, we drop about 0.6.7 volts across this diode. As the batteries are charging, they're drawing current that's going to lower the output of the adapter some. We're also dropping some voltage across this resistor, so we'll wind up with 6-ish volts across here. That's all there is to it. It has no idea how charged the batteries are, etc. If you think, hey, I'll just take the batteries out and plug my adapter in here, well, the problem there is that the batteries are not here providing a load, and it's not loading down the adapter. So you're going to get much more than our 6-ish volts right here. And on some equipment, that can damage it. Now, what you could do in this case is, if you wanted to run it without the batteries, is remove the battery pack, apply 6 volts here. With a modern adapter, you're going to lose a little across this diode, like I say, about 0.6, 0.7 volts. So a little across this resistor, but you'll still wind up with a little more than 5-ish volts here, which is about what you would have from the battery pack. That is one solution that will work, and it'll be safe. What do you do if you want to charge up your HX20 or similar vintage computer and you didn't get the original unregulated adapter? Well, we can buy various wall warts, and even ones that are multiple voltages with the range of tips like this that you hook to it. And these have your standard voltages, 12 volts, 9 volts, 6 volts, etc. And they have some that are kind of in between, like 7.5 volts and 4.5 volts. Now, we learned from our experiment on the bench that we could make a regulated power supply act very much like our unregulated by adding a resistor in series. So we found out that our original power adapter was about 8.5 volts open circuit. It produced 6 volts with a 400 milliamp load for a difference of 2.5 volts at 400 milliamps. And we did a little bit of math, and we found out that if we put a 6 1/4 ohm resistor in series, then our regulated power supply acted like the unregulated. Now, with this modern regulated power supply on the 7.5 volt setting, we're only going to have 1.5 volts difference. So if we redo our math here, we find out if we put about a 3.75 ohm resistor in series here, we could make this guy act very much like the original power adapter. That does require a little wiring. Maybe you want to make an adapter plug with the resistor in there. You'll have to calculate the power requirements of the resistor. Power equals the current times the voltage, or power equals the current squared times the resistance. In this case, it's just under 1/4 watt. I would probably use a 1/2 watt resistor just because it depends on the requirements of your particular device. Our next machine is this Epson PX8. It uses the same sort of battery pack the HX20 did, and it also has a 4-cell 4.8 volt memory backup battery. And the charging circuitry in the PX8 looks really fancy, but basically all they've done is use a timer to automatically cut off the charging of the battery after 8 hours. So you can jumper that to turn it on, move the jumper over here, and there's no time limit on the charger. So this isn't actually cutting off the charging based on the battery condition. It's just cutting it off with time. It's pretending to be you unplugging the adapter. This machine is going to be more difficult to run without batteries because it has that internal memory battery, because it has things like a RAM drive, etc., where it's keeping track of things. You can use the same sort of adapter that we used with the HX20. When I first started working on this machine, I took the battery pack out because it's easy to do on this machine. I charged it with my bench power supply set to 6 volts. So it's a 4.8 volt NiCad pack charged at 6 volts. The initial charging current was, close to 100 milliamps, which is a little high, but still okay. And it quickly dropped down to 50 or 60 milliamps and then tapered off. So that was a decent charging voltage when monitoring the current and watching it for time. Now, when I put the battery pack back in the machine, I tried just for fun connecting the 6 volts to the jack here, but of course we have our resistor and diode in here. So we took our 6 volts regulated from my bench power supply. We're dropping 0.6 or 0.7 volts here, plus whatever we're dropping across this resistor, and that was not enough to effectively charge the battery pack. It was down to only about 10 milliamps or so charging, which would take a long time. Not very practical. I bumped the voltage up to 6.5 to 6.75 in that range, and it charged fine. In that range between 6.5 and 6.75 volts, the voltage inside the machine was acting like what we would see with this sort of original adapter plugged in. A little bit came to check out what was going on, supervise and dig in the trash. Say hi to everybody a little bit. Yes. Okay. I think she wants to go outside. I'll be right back. Okay, here we have another machine, or actually two. We've got the TRS-80 PC2 pocket computer plugged into the printer and cassette interface. This is the same thing as a Sharp PC1500 and CE150. Now, the computer itself runs on 4 AA batteries. There is nothing rechargeable in here, and it's kind of interesting for a pocket computer that it actually has a voltage regulator module here inside. So we've got our 4 AA batteries. We go through a diode. This is a germanium type diode, so it only has about a 0.3 volt voltage drop into the voltage regulator, and we get our VCC out. You also notice this V battery connection. Will come to where that comes from in a bit. And we have these dotted lines here which say adapter jack. There are 2 diodes here, and that's kind of spliced in past this diode with the AA's. So the reason for these 2 diodes, these are going to drop about 0.6, 0.7 volts a piece. So let's say 1.4 volts. Our adapter, this plugs in here, we're going to drop, close to 1.5 volts across these diodes. And we're going to be at this point down to a safe voltage that this voltage regulator can handle. We'll see this many times in schematics. When you look at it, they'll be using diodes as a precise-ish voltage drop in some cases, as well as reverse polarity protection. The cassette printer interface is completely different though. It looks like this because it has a 5-cell NiCad pack, so 5 times 1.2 volts, 6 volts. We have our adapter here, and we notice that if we're powering with the adapter, we're going to go through this resistor to charge the battery. Okay. Powering from the adapter, we are going to go through these 3 diodes for some voltage drop before we get to the motor power for the device. If we're powering from the battery, we're only going through 1 diode because our battery pack voltage is lower than the adapter voltage. And here we see this VBAT. Now, some people, they don't want to put a battery pack back in this thing because, after 40 years, the batteries, some of them go bad and it ruins the inside of the machine, and they're like, well, I'm not going to put a pack back in there, so they'll leave this pack out and they'll plug in an adapter that's the original rated voltage, but without the pack in here to lower the actual voltage. At this point, you're actually applying a little too high a voltage to this stuff inside and to this VBAT connection, which you remember runs to here and will actually power the PC2 when it's plugged in. So when the PC2 is plugged into the CE150 the cassette printer interface. This will power this. So it's the problem with, again, with the battery pack not being there to load down the adapter, and we'll have too much voltage getting to things. Now this adapter, the one from Radio Shack, is rated at 9 volts, 500 milliamps. The one from Sharp was something like 8.6 volts, something really odd. You could plug this directly into the computer, and with this, the couple diodes here and the voltage regulator, everything was fine. When you plug that into the printer cassette interface, we've got a 27 ohm half watt resistor in series, and of course we're not going to have 9 volts then. It's going to, you know, drop to maybe closer to 7.5 volts to charge our battery pack. And again, this is a time-controlled charging system. It says in the manual to charge 8 hours or overnight. And some people back in the day thought, well, I'll just keep this plugged in all the time, right? And that way I won't use up my batteries. But what they wound up doing was boiling the battery pack dry because it was charging continuously. With these, if you don't want to run with the battery pack in here, I would use an adapter that is, I don't know, maybe 6 volts, but the problem is you're going to be dropping some voltage across these 3 diodes. You might be able to use one of the 7.5 volt adapters, and that's going to give you 7 minus 1.5, about 6 volts here, which would be about the same as the battery pack, and that would be a lot better than using the original 9 volt adapter, which I don't know that they have damaged things, but they could. And because of the motors here for the printer, they draw huge surges of current, which the battery pack can handle, but you'll need more than a 500 milliamp adapter for that, maybe something closer to an amp. And we have portable computers like this Tandy 102. They run on 4 AA batteries, and they also have a very small, like 80 milliamp hour memory backup battery. It's an iCAD battery. Our circuit diagram looks like this. This is the memory battery, but you can see it's charging through a 1.8K resistor plus the reverse polarity protection diode. So it has a really, really tiny trickle charge, so it's not as easy to damage it or overcharge it. And since most people are using these kind of in a not plugged in mode, that's okay. Here is our 4 AA cells right here. Now, since on this thing we are not charging it by plugging the adapter in, we can go, we have a little more freedom. Now, this says 6 volts right here. And, if we follow the schematic diagram through, we go into all this mess right here, which is actually a DC to DC converter, which will take our battery voltage or the adapter voltage and convert it to what the machine needs. So we're not in as big a danger of overvolting the insides of the machine because we have our DC to DC converter here to take care of that thing for us and generate the proper voltages that we need. So even though this original adapter would have been unregulated, we've got a regulator built into the machine that will take care of that for us. So we can use a modern 6 volt regulated adapter. Will probably do just fine. It might make the DC to DC converter run a little more. Or you could do something like one of these multi-voltage adapters, even set to 7.5 volts, and that would probably work as well, but I would probably just use 6 volts since this guy can handle it. And you can find a regulated 6 volt wall wart, no problem, and have a dedicated adapter for your machine. So the big thing with all of these, make sure you have the polarity right. You see that's not written on here what the polarity is. Some machines will be nice enough to do that. It's not written on the back of the machine. Now, I know off the top of my head, because I've worked on so many of these, that these are center negative. If you're unsure and you can't find the schematic for your piece of equipment, A lot of times you can measure from the center pin to a ground or common point in the machine and see if there's continuity there, see if that's a dead short. If it is, you found your ground connection. That's a good way to do that. Oh, bash the camera. Sorry, camera. I hope this has helped point out some of the considerations when you're choosing a modern power adapter for your vintage gear. There are some pieces of equipment like this Model 102 here where we're not trying to recharge any NiCad batteries inside, and it has a DC to DC converter, so we could use an unregulated or regulated 6-volt power adapter and it'll work just fine. And we have other machines like this Epson HX20, which we do have a NiCad battery pack inside, and there are other things we need to consider there. And the primary thing being that we can't just use the original adapter with the battery pack deleted and hope that it works. There are some machines that will blow things up because we're not loading down the original unregulated adapter. The voltage applied to the machine will be higher, and that's bad news. There are other machines like the PC2 we looked at where the PC2 and the printer cassette adapter worked a little differently. So the thing is, you need to know a little bit about the machine to decide what type of modern power adapter that you can use. And we even figured out how to make a modern power adapter work like an vintage unregulated adapter by adding a resistor. If you have any questions or comments, I would love to hear from you. Just leave those in the comment section down there below. Thanks to everyone who helped support the Hey Birt channel through Patreon and other means. It's greatly appreciated. Well, until next time, bye.